Welcome back to the class. In this session, we will discuss about the text compression techniques. Text compression techniques has to follow one of the lossless compression technique. What is lossless compression? The output of the decompression algorithm should be an exact replica of the data given by the information source. The source encoder has to perform the compression algorithm in using that principle. So, in the text compression, we have the static coding as well as dynamic coding. So, static coding, the encoder has the complete knowledge of, in the static coding, the encoder has the complete knowledge of the characters being transmitted. So, in that the first category we are going to see static HUFFMAN coding. This coding algorithm compression algorithm or coding algorithm we can explain with an example. Assume the text Q. This text has to be compressed by the source encoder using our static HUFFMAN coding algorithm. So, static HUFFMAN coding algorithm, at the first step, it analyzes the text. It analyzes text and find the number of characters in the text. How many characters are there? There are totally 5 characters are there. And then probability of occurrence of each character will be found. So, totally how many different characters are there? 3 distinct characters. Q is one character, U is another character, and the probability of E. So, how out of these 5 characters, how many times the Q has occurred? Only once. Therefore, 1 by 5 is the probability of this one. So, that is 0.2. And how many times the character U has occurred? 2 times. Therefore, its probability is 2 out of 5. That gives the value 0.4. Similarly, the E is also occurred 2 times. Therefore, its probability is 0.4. After finding the probability of each characters, the HUFFMAN coding algorithm arranges the symbols in the descending order with respect to the probabilities. So, among these, which has the highest probability? U and E. Either U or E can be placed at the top. So, let me place the character U, E and then Q. And its probability is, the probability of U is 0.4, E is 0.4 and Q is 0.2. That is, it is in the descending order with respect to the probability of occurrence. And then we need to do a splitting stage. How will you do this? The last 2 symbols are to be combined together. And what is a combined probability? 0.4 plus 0.2 is 0.6. And for the higher symbol you are assigning 1 and the lower probability symbol you are assigning 0. And this newly combined symbol has to be placed, and the newly combined symbol has to be placed in the list in accordance to its probability. Again, the descending order has to be followed. Therefore, this 0.6 has to be placed at the top and this 0.4 has to be placed in the next symbol. Again, these two are to be combined. So, this is 1, this is 0. So, what is a combined probability? It is 1. So, till the combined probability becomes 1, this step has to be proceeded. Now, we are going to derive the code word for this symbol. So, I am again putting this character, probability, the code word. So, what are the characters we have? U, E and Q. You have to read the tree from left till the end. At the first stage, have you assigned any binary bits for this? No. And you follow this path and then at this stage it is assigned 0. Therefore, the character U is assigned the this one code word 0 and its probability is 0.4. And for E, the probability is 0.4. Again, you follow the path of E, the tree. E at this stage, it's assigned 1, and at the next stage, you follow the path. And at the next stage, you have assigned 1. So, you have to reverse it. So, 1 and 1. Therefore, when you are reversing also, you will be getting 1, 1. Next, we follow the character Q in the tree. At the first stage, 0 is assigned and the combined symbol is moved here. Therefore, 0, 1 is its path. Therefore, you should write it in the reverse. Therefore, 1, 0 is its code word. Okay, right? You observe it. This 0.4 is a high probability symbol. It is assigned lesser, shorter code word. 0 is a lower probability symbol. It is assigned lengthy code word compared to this. Okay, now we will see how many bits we have saved. How much, what is compression? Process of reducing the volume of information to be transmitted. Okay, so if I have not used the compression, how many bits I might have transmitted without compression? That means without compression. That means assume I am using an ASCII coding. In ASCII coding, we are using 7 bits per character. So, totally how many characters? For all the characters, irrespective of the probability, for all the characters, 7 bits are assigned. Totally how many characters are there in this string? 5 characters are there. Therefore, the total number of bits required are 5 into 7. So, totally 35 bits are required to transmit this Q, the string, to transmit in the network through an ASCII. It requires 35 bits. But we have used our static HUFFMAN coding algorithm. In that, for character U, you have used 0 and E 2 and then Q 2. Therefore, the number of bits required are required in HUFFMAN coding. Character Q has occurred only one time. So, one time, and how many bits are required? 2 bits. So, here code word length we will find. What is the length of the code word? 1, 2 and 2. Okay. And then probability of U, that is U into 1, that is U is only one time it is occurring, and then E has occurred 2 times and its value is 2. Therefore, 2 plus 1 plus 4. So, totally you have required 7 bits. Okay. So, for Q has occurred only one time and it required 2 bits. And U is also occurring 2 times. And how many bits are there? 1 bit. And it is 2 times occurring 2 bits. Therefore, totally 8 bits are required. So, how many bits you have saved? It is requiring 8 bits and it is requiring 35 bits. So, number of bits saved is 27 bits we have saved due to this compression. Okay. So, this is our static HUFFMAN coding. Now, we will see how the tree is being constructed. You see it in the reverse way. I have drawn it in the landscape wise. If you are tilting it, so how this tree will be? So, at the top you will have 1 and then here you have, this is 1, 0 and this 1 is splitted into 2, it is 1, 0. To the 1 branch you have assigned E and to the 0 branch you have assigned Q and here you have assigned this U. So, this is our HUFFMAN tree. In this HUFFMAN tree, this node is referred as a root node. And once the characters are assigned, they are referred as a leaf node. and the node which is having the branches, it is referred as a branch node. So, root node, leaf node and branch node, and the values are indicating the weightage of that branches. So, by observing the tree, you can tell what is the code word for U. Just read the read the tree from the root node. So, 0, 0 is the code word. And then for E, read the tree from the root node, follow the path. So, 1, 1 will be the code word for E. And then observe the character Q from the root node. Therefore, 1, 0 will be the code word for the character Q. Okay. And the same Q is the string, but still more the characters are arriving. By that time, how the HUFFMAN coding works? Now it takes in hand this dynamic HUFFMAN coding principle. That we'll see now. Okay. Now we are going to see the dynamic HUFFMAN coding. What we are going to see? Dynamic HUFFMAN coding. In dynamic HUFFMAN coding, the encoder and the decoder builds the tree dynamically, and it doesn't have the complete knowledge of the characters in the string. Okay. So, it builds the tree dynamically. Both encoder and decoder. Both the encoder and the decoder build the tree dynamically. Now we'll see this dynamic HUFFMAN coding for the same example Q. As far as the encoder is concerned, now only we are typing the character Q. Okay. The algorithm starts with one root node and one empty leaf node. This empty leaf node is assigned 0. That means its probability of occurrence is 0. So, this is my tree, and this is an information transmitted in the dynamic HUFFMAN coding. First, the tree has one empty leaf node assigned to the 0 branch, and this is known as my leaf node, and this is the root node. Now the encoder receives the first character Q. It receives the first character Q. Then what it does? It assigns that first character into the one branch. So this is my root node, and this character Q is assigned to the one branch. As it is the first time this Q is occurring, its probability of occurrence is specified at the bottom of the suffix of our character. So Q1. So the probability of occurrence is 1. So what is being transmitted to the receiver? The Q is transmitted in ASCII form, as it is the first time of occurrence of the string, characters in the string. Next we are going to see what is the second character. U is the second character. What this encoder does, it examines the tree and identifies whether it is a new character or not. When it is not a new character, again it splits the empty leaf node into a branch node. It splits the empty leaf node into a branch node and redraw the existing one. Q1 is assigned to one branch, but this empty leaf node is splitted into a root branch node. Again the empty leaf node is assigned to the 0 branch, and one branch the character U is assigned, and it is a first time of occurrence. So here also it is specified as U1. Always you see that empty leaf node is assigned to the 0 branch only. Now what is being transmitted to the receiver? To the receiver, position of the empty leaf node present in the previous stage. Position of empty leaf node of the previous stage. So in the previous stage, what is the position of empty leaf node? You should read it from the root node. So its value is 0. And then the character in uncompressed form. The character in uncompressed form. In uncompressed form. So that is like ASCII. So 0 and U in ASCII. Okay. And then before proceeding to the next stage, you should check the weightage of each nodes. Here 0 and 1, only one character is present. Therefore, the weightage of this root node is 1. And then this 1 and the 1 character is there. Therefore, the weightage of the root node is 2. That indicates totally 2 characters have arrived. Now we are moving to the next character. That is U is our next, E is our next character. What does the encoder do? The encoder checks the tree whether it is a new character or an already existing character. As it is a new character, again the empty leaf node has to be splitted into 2. First you redraw the tree as such. So it is Q1, 1 branch, 0 branch, 0 branch, 1 branch, and it is U1. This is our empty leaf node. Now it has to be splitted into 2. This empty leaf node has become a branch node now. And the empty leaf node is assigned to the 0 branch. And then the character E is assigned to the 1 branch. Therefore, what will be the weightage of this branch node? Here it is 0 plus 1, 1. And how many characters are assigned? Only 1 character, and the weightage of this node is 1. Therefore, the weight of this branch node is 1 plus 1, 2. And then what is the weightage of our root node? 2 plus 1, 3. So, as far as the character is concerned, you should see the probability of occurrence. As far as the branch node is concerned, you should see the weightage of that node. That is, how many characters are under that branch node. That's why here 2 is the weightage of the branch node, and for the probability the occurrence is 1. Therefore, 2 plus 1 is 3. So, now what has to be transmitted to the receiver? The position of, as in the previous step, the position of empty leaf node of the previous stage. As far as this stage is concerned, this is our previous stage. In this previous stage, what is the position of our empty leaf node? Read it from the root node. Therefore, 0 and 0. So, this is our position of empty leaf node. This is only the weightage of the branch node. I am seeing only the labels assigned to the labels assigned to the branches. Therefore, 0 and 0 is the position of empty leaf node, and the character E in ASCII waveform. And before proceeding to the next stage, you should find out the wait list. How will be deriving a wait list? Wait list is derived by reading the tree. Wait list is derived by reading the tree from left to right, from left to right, and from bottom to top. In this way, you have to read the tree. So, if I am reading it, what is the wait list? E0, E1, 1, U1, 2, Q1, 3. Reading the tree from left to right and from bottom to top. Therefore, what is the wait list here? Wait list for this stage is E0, E1. The first stage is over. The bottommost level is over. Next, move to the up level. So, here what is our leftmost node? This is 1 and our right is U1. Therefore, 1, U1. So, this level is also over. Move to the next level. 2. Leftmost node is 2 and rightmost is Q1. Therefore, 2, Q1. And then move to the next stage. Only 1 is there. Therefore, 3. Now, observe the wait list. It has to follow an ascending order, that is optimal tree. In optimal tree, the wait list is in an ascending order. Wait is in an ascending order. Therefore, is it in the ascending order? No. Therefore, you need to do the swapping. With a minimal number of swapping, it has to reach the optimal wait condition. Therefore, the 2 and U1 are swapped. Therefore, the optimal wait tree is E0, E1, 1, 1, U1, Q1, 2 and 3. Now, again the tree has to be drawn. That is the updated tree has to be drawn. This is our optimal tree. Otherwise, we will name it as an optimal tree. So, how will you create an updated tree? Read the wait list. Read the wait list. Construct the tree. Construct the tree from top to bottom and from right to left. It is just the reverse of our wait list construction. Read the wait list. Okay. Read the wait list from right side, right end. Therefore, this is my wait list. It is my wait list. So, for this updated wait list, read it from right end and construct the tree from the top. Therefore, topmost value is going to be 3. Only one value is there. Now, you split it into 2. What is our next value? Right to left. Therefore, the right value is 2 and the left is Q1. Be clear. Once the character is assigned, then that cannot be a branch node. It is named as leaf node. Therefore, now the Q1 has become a leaf node. You cannot further branch it. Whereas, this is the weightage. Therefore, this can be branched. This node can be used as a branch node. So, after Q1, what you have? U1 is assigned to the right branch and 1 is assigned as a left branch. Here also, the character is assigned to this node. Therefore, this node will be now termed as leaf node. That cannot be further splitted. And this node can be splitted into 2. So, after this one, what you have? This is our E1, this is our E0. Now, assign the labels to the branches 0, 1, 0, 1. Always left branch is 0 and right branch is 1. Okay. Now, you check the weightage of the branch nodes. It is 0 and it is 1. So, 1 is there. Fine. And this the weightage of this branch node is 1 and this is 1. Therefore, this node will have the weightage 2. Fine. And then 2 plus 1, 3. Therefore, it satisfies the condition. Now, we can proceed to the next stage. Okay. What is our next stage? The next character. Now we have processed for the character Q, character U and the character E. Now the next character of the string is U. Whether it is an existing character or the new character, it is an existing character, right? So if it is an existing character, you have to increase the probability of occurrence of that character. Clear? In the previous two cases, the character was the new character. By that time, the character is assigned to the 0 branch. 0 branch is splitted into a branch node, and then you assigned the character to the 1 branch. Whereas, if it is an already existing character, you should increase the probability of occurrence of that character. No need to do any modification in the empty leaf node. Therefore, now what will you do? For the character U, okay. Now the character is U. Character is U. Therefore, you redraw the tree of the previous stage as such. Therefore, it is Q1, it is 2, U1, 1, E0, E1, it is 0, 1, 0, 1, 0, 1. I have simply redrawn it, but as this U character is an already existing character, therefore increase the probability of occurrence of U. Okay. Therefore, the U has been, this probability has been modified as U2. Now we check the weights. This will be fine, 1. But this is 1 plus 2. Therefore, the weightage of this branch node is 3. 3 plus 1, 4. The root node, the weight of the root node always indicates total number of characters encountered by the or received by the encoder. Okay. From the information source. Therefore, totally 4 characters have been received. Okay. How come this will be intimated to the receiver? By sending the binary string, right? Therefore, now, so far, it is a new character means you transmitted the position of empty leaf node in the previous state and the character in the ASCII form. Now, what you have to transmit? Position of the character we should transmit. Position of the character is transmitted of the previous stage. So, what is the position of the character in the previous stage? The U, you read it from the root node, therefore 1 and 1. Therefore, what is being transmitted? 1, 1 will be transmitted. Clear? Now, before proceed to the next stage, again we have to write the weight list. Okay. How will you write the weight list? Yes, right. Reading the tree from left to right and from bottom to top. Therefore, what is the weight list? E0, E1, this level is over, move on to the next level. 1, U2, this level is over, move to the next stage, next level. Q1 and 3 and the next level is 4. You observe the weight list, whether it is in the order? Definitely not. Therefore, we need to do the swapping. I am doing the swapping of this one. Therefore, E0, E1, 1, Q1, U2, 3, 4. Now, are you ready to construct the tree? Right. How will you construct the tree? Read the weight list from the right and construct the tree from top to bottom and from right to left. This is the formula. Top to bottom and from right to left. Therefore, what is my topmost node will have? The weight is 4 and split it into 3. The rightmost node is 3 and then you have a U2 and this character U is assigned to a node. Therefore, it becomes leaf node now. Now, this 3 is splitted into 2 and after U2 what you have? Q1 and this is 1. The Q1 is assigned here, therefore, it becomes a leaf node. Now, this 1 is splitted and this is E1 and this is E0, 0, 1, 0, 1, 0, 1. Now, observe the values. This branch node has only one character. This branch node has totally 2 characters. Therefore, you modified this weightage as 2. And 2 plus 2, this is branch node weight is 2 and the number of characters here are 2. Therefore, totally 4 is over. So, now it has become an updated tree or a what we will name it as an optimal tree. Okay. With this thing is not over. What is the next character to be received? E is the next character to be received. Okay. Now, the character is E. It is the tree. It is information to the receiver. To the receiver, we are transmitting only the code. Binary string alone is transmitted, nothing else. Therefore, the character is E. And whether it is a new character or an already existing character, it is an existing character. Therefore, what will you do? You will simply increase the probability of occurrence of that character. Therefore, you redraw the updated tree. Be clear, you redraw the updated tree. Therefore, I am simply copying it here. Right? U2, 2, 0, should not 0, this one, 1, Q1, E1, 0, 1, 0, 1, 0, 1. Okay. Now, what will you do? Increase the probability of occurrence of E. Therefore, it becomes 2. Now, what will be the weightage of this branch node? Totally 2 characters, therefore 2. 2 plus 1, therefore this becomes 3. 3 plus 2, it has become 5. We have drawn a tree. Okay. Now, what will be transmitted to the receiver? Position of that character in the previous stage will be transmitted. What is the position of the character E in the previous stage? You read from the root node, therefore 1, and then you will follow this path to reach our E. Therefore, you follow the labels 1, 0, 1. Therefore, 1, 0, 1 will be transmitted. That's it. 1, 0, 1 alone will be transmitted. Now, what is the wait list? Wait list, read the tree from left to right and from bottom to top. Therefore, E0, E2, 2, Q1, U2, 3 and 5. Okay. So, now what happens? Is it following our optimal wait list? No. Therefore, I am swapping it. Therefore, E0, Q1, 2, E2, U2, 3, 5. Okay. Do you know why we are doing this swapping and all? To create an optimal waitlist. That means our Huffman coding follows the principle of variable length coding. That is, frequently occurred characters are assigned lesser number of bits. Rarely occurred symbols are assigned lengthy code word. That is more number of bits. Therefore, to bring up the frequently occurred characters, that is based on the probability of occurrence, you are bringing up the characters towards our root node. When it is approaching our root node, automatically the number of bits required to reach that node will be lesser, will become minimum. That's why we are doing this. To do that only, we are doing this swapping and we are drawing an updated tree. All these are being done by whom? By the encoder. The source encoder sitting in the transmitter side is doing all these functions. Okay. Therefore, what is our updated tree? How will you draw? Read the wait list from the right and construct the tree from top to bottom and from right to left. Therefore, 5, split it is into 3 and U2, 3 is splitted, E2 and 2, 2 is splitted, E0 and Q1. Therefore, this becomes 1, 1 plus 2, 3, 3 plus 2, 5 and assign 0 and 1 to all the branches. Okay. So, with this, the encoder has completed the coding part of our queue. The queue has been transmitted like this. Okay. Now, we will see how many bits have been saved by the compression algorithm. Okay. That will work out now. Queue. If I am using an ASCII coding, Totally how many characters are there? 5 characters. Therefore, number of characters are 5. And how many bits are required if you are using ASCII coding? In ASCII coding, 7 bits per character. Okay. Therefore, totally how many bits are required? Total bits is 5 characters, for each character 7. Therefore, 35 bits as we have seen in the static Huffman coding. In the dynamic Huffman coding, while transmitting Q, as it is a first character, how many bits you transmitted? 7 bits. When you are transmitting U, how many bits you transmitted? 1 is the position of empty leaf node. For that, you required 1 bit. And then 7 bits. You observe the tree and 7 bits for your ASCII. And when you are transmitting E, how many bits required to represent our position of empty leaf node? It took 2 bits. Okay. So 2 bits plus 7 bits. And again U. How many bits you required to transmit U? Only position of that character. Therefore, 2 only you required. And then for E also, how many bits you required? 3 bits. So you sum it up. So 7, 15, 22, 24, 26, 29 bits. So how many bits you have saved? 6 bits you have saved. But be clear, every character is coming one by one. Based on its arrival only, it is assigning its position in the tree and it is transmitting the bits. Clear? So in static Huffman coding, you will have the complete knowledge of the entire string, whereas in the dynamic coding, it is done time to time. This tree is updated dynamically. Okay, so that's all about our dynamic Huffman coding. That is our text compression technique.